Okay, welcome back. Last time we finished talking about basic elements of robust control. We had a system given by a scalar and for a differential equation where the state was here. And we were interested in tracking some desired trajectory with a tracking error defined by xd minus x of t minus xd of t. We said we would first replace this original nth order problem by a first order problem. And this would be done by using an intermediate variable, which we called s, for instance, defined as such. And this variable had two properties. One that s dot contained u, and therefore we needed to differentiate it only once to find the control input. And two, that s tends to 0 implied that x tilde tended to 0. In other words, that we had achieved the original trajectory tracking problem. So we had solved the original trajectory tracking problem. So we saw also that there was uncertainty in f. If there was no uncertainty in principle, we could just exactly cancel f and replace it by something simpler. But there was some uncertainty in f, and this uncertainty was in the form of the fact that we only had available an estimate f hat of f. And how good this estimate was quantified by something else we knew, which was this capital F quantity. We then saw that if we wanted to achieve this tracking error, tracking error tending to 0 in the presence of this uncertainty, we could use a u which had this form, u equal u hat minus k sine of s, which in principle allowed to achieve achieve 0 tracking error in the presence of this uncertainty capital F, provided we chose k equal capital F plus eta, where eta was a small quantity which we needed to satisfy the so-called sliding condition, and F was the real thing, which was, again, quantifying the uncertainty on the dynamics. So, so this is what we had, and we said, if you have certain systems like Palfwitz modulated electric motors, for instance, this might be all you need to know because you can implement control laws like this, and they work extremely well. In most systems, though, this term is a problem because it creates control chattering. And so we said we would replace this by the same u hat, the same k, but now some interpolation into a boundary layer, in a boundary layer. And we explain how to choose phi, perhaps time varying, to pick reasonable choices, as also we explain how to choose lambda. So the idea was that instead of tending to this surface in finite time and then sliding along it, you tended towards the boundary layer in finite time and then stayed in it, which in turn implied performance bounds on the tracking error. And again, we talked more about how to choose phi, constant or time varying, and also how to choose lambda. So today, we're going to go one step further than this and say, okay, so this was our model of uncertainty f hat minus f equal less or equal to something we know. We're going to say, well, what if we can say a little more about f hat minus f? Specifically, are there elements in f hat minus f which depend only on unknown constants? For instance, in f hat minus f, is there a term like a times cosine x, where, you know, I know cosine x, of course, but I happen not to know a, but I just know it's a constant. All right? So the question we're going to ask, which is so-called the adaptive control question, is how to exploit the fact, or the possible fact, that part of the uncertainty in the dynamics f of xt can be described simply as unknown constants. Again, you know, f is let's say a cosine x plus a bunch of things, and a is an unknown constant. So there, up to now, we would say, well, can you give me bounds on a, and I'll try to bound this term and get rid of that from a robust point of view. But what we're saying is perhaps we can do better than that by exploiting the fact that a is an unknown constant, okay? Basically, can we make the system work as if the unknown constants were known? Now, what's the motivation for that, of course, is that if you, for instance, get back to this formula or even this formula, right, you see that the extent of this either sine term or saturation function term, and therefore the size of this boundary layer, and therefore the quality of the tracking you can expect, okay, which, you know, the larger the boundary layer, the least you can guarantee about the tracking, okay? We have explicit formulas for that, okay? So if we somehow manage to exploit the fact that we have these unknown constant and somehow design an algorithm that makes the system work as if these unknown constants were known, all right, it means that k is going to be smaller, because basically this a cosine x won't appear in there. And because k is going to be smaller, if you remember the equations for phi, okay, or reasonable equations for phi, right? We had said something, for instance, like phi dot plus lambda phi equal k sub d. Phi is going to be smaller as well, right? So the boundary layer is going to be smaller, so the tracking performance is going to be better, all right? So the motivation is perhaps there's a way to manage the unknown constants as if they were known. This will accordingly reduce capital F, and therefore k, and therefore phi, and therefore x tilde. Okay? So why think about that? Because actually, in linear systems, although sometimes presented in a reasonably clumsy way, but in linear systems, you've already seen something like this. You've already seen an instance where we have a system and there's an unknown constant in this system, and we make the system work as if the unknown constant was known. Okay? And by the way, we'll generalize this and we'll make it work well as if the unknown constant was known. But have we seen anything like that in linear systems? You have a system, you have an unknown constant, and you try to make the system, you have a stabilization problem, you're trying to make the system go to 0, and we're trying to make the unknown constant, the system behave as if the unknown constant was known. Yes?
Well, you can reject. If you know the frequency, you can reject a disturbance.
If you know the frequency, okay, but I'm talking about the constant. Yeah, sure.
In front of the customer.
Oh, okay, so sorry. Yeah, that will do. But I'm saying just in linear system, this is cosine x, right, not cosine t. But yes, we can, right? But I'm just saying in linear time invariant systems, right? Have you seen anything like that? Well, that's what an integral control does, right? Integral control, you have a second order system and you had a constant disturbance, right? And the point of the PID, the I in the PID, is to make the error be 0 even in the presence of this constant disturbance. Okay? And there are more or less clever ways to do that, but basically that's the point of the PID. Okay? So here, of course, we have a linear system, so it's not going to be A cosine x because x is the state, right? But it could be just A, and A is a constant, and we call it D-like disturbance, right? And we're trying to reject that, all right? So the reason for considering this idea, if you want, is not just to say, well, you know, let's try constants and then let's try other things, you know, is because we know already that in the linear case, there's a way to handle constants. All right, so we're going to say, okay, in F, there are these things described by unknown constants, and that's the rest, okay? So to introduce these ideas, I'm going to take an example where everything is described by unknown constant, okay? There won't be no, you know, time-varying rest, okay? Everything is described by unknown constant to give you, you know, to explain how it works, and then, of course, it will extend very easily to the mixed case, which we'll see later on. So let's see this, okay? So this is a very simple example. It's basically a pendulum. If you want to make it sound more fancy, you can say it's a one-link robot, okay, with a load, okay, an unknown load, okay? But it's a pendulum, right? And the angle, so this gravity, right? The angle that this system has with the vertical is described by x, and there's a motor here, okay, and this motor is applying some torque, which we'll call u. So we have a pendulum, you know, the angle with respect to the vertical is described by x, and we have a motor where we apply some torque u. So what are the equations of this system? Well, it's F equal ma, right? So it's jx double dot. Just for fun, we're going to assume, just to see that, you know, you can add nonlinearities. It doesn't really matter. So just for fun, we're going to assume that this thing is underwater, or you know, there's a, you know, strong viscous effects, which we model simply as drag terms. Okay, this is just to put a nonlinear term. And then we have the gravitational torque, which is going to be mgl sine x. And the whole thing is going to be equal to the motor torque, which is u. Okay. So the story is still, we are interested in the tracking control problem, okay, in having x tilde tend to 0. We have uncertainty f hat minus f, except here all of the uncertainty is in the fact that neither the inertia of the system, nor this damping coefficient, nor the mass and position of the center of mass of this link are known. All right? So basically, J, B, M, and L are all unknowns. Okay? And we're trying to make this system follow an arbitrary trajectory, you know, maybe do something like this, whatever we specify. Okay? So, first question, from a control point of view, we're going to need to design a controller. We design a U for this, right? How many unknown constants are there? So we don't know J, we don't know B, we don't know M, and we don't know L. And therefore, there are 3 unknown constants, right? Because we have this A, right? A1, A2, and of course we don't, in here, we don't really care about what's M and L, right? What we care about is MGL. So let's say 3. Okay, so we have 3 unknown constants. Whenever M appears in this equation, so does L, and conversely, or so is just MGL. Now, this is a little trivial here, but in the general robotic case, you'll see these constants are more sophisticated, but they're always mixtures of known parameters. Okay, so we're trying to get the system to follow a desired trajectory in the absence of any information on these constants A1, A2, and A3. So, first of all, of course, there's no reason to throw away good ideas, okay? So we can still say, this is a second-order problem. I'm going to first replace it by a first-order problem because it's likely going to be simpler, okay? I measure the state. And so how am I going to do this? I can still do the exact same idea, which is I'm going to define an intermediate variable s of the form x tilde dot plus lambda x tilde. And this S will satisfy exactly what it's satisfied here, namely, I've replaced an nth order, in this case, a second order problem, by a first order problem. Okay? Just because we're going to use this idea in various forms, we're going to introduce an extra notation to kind of belabor this point, if you want, that S dot contains U. Which is in here, we're going to say, well, you know, this is x dot, and then the rest, which I'll call minus x dot r. Okay, so in other words, this is just defining x dot r. And if you think about it, what's x dot r? Well, simply x dot decide minus lambda x tilde, right? Okay, so it's the same thing. I've just introduced an extra notation, which I call x dot r, which is whatever is in S which is not x dot. Okay? And since we're there, we can define x double dot r. So this is just a notation, right? We could call it Mickey Mouse. So we decide to call it x dot r. There's no xr, right? It's just a notation. Okay? And similarly, we can define x double dot r to be, of course, the derivative of x dot r. That's also a notation, which is x double dot decide minus lambda x tilde dot. Okay? So we have two notations, x dot r and x double dot r, which of course we define as being the derivative of x dot r. If we measure the state, both of these quantities are known, right? The desired trajectory and its acceleration is known, and we know, of course, the state, the position x, and the velocity x dot, right? So to compute this, we need to compute x dot r and x double dot r, we need only position and velocity of the real system, and decide position, velocity, and acceleration. Okay, so here we are. We've just introduced the same idea here because we're still interested in making the problem simpler. And you know, in homeworks, you'll have a third order system. It will just be just as simple because you'll introduce this notation, and so it will be the same. So now, what kind of, so when we played with robust control and sliding surfaces and so on, we kind of had a homemade Lyapunov-like function, which was s square, okay? Here we're going to do something very similar, except we're going to need a slightly more general tool as well. So out of the tools we studied in Lyapunov theory, Lyapunov theorems, invariant set theorem, Barballa's lemma, which one are we likely to be using here if we use anything beyond, you know, s square? Well, it will be a non-autonomous system, right? Because we have this desired trajectory xd of t, right? So actually, the only thing we've seen on non-autonomous systems, right, is Barballa's lemma, right? So that's likely that's what we'll be using, okay? So we have a non-autonomous system. we're going to try to prove things about convergence and stability and so on, so we'll use actually Barbaro's lemma. So we'll need to come up, remember, with a function v of xt such that v is lower bounded, v dot is negative, and v double dot is bounded. Okay, which then will imply that v dot tends to 0. Okay, so that's what we'll do. But let's just start for the moment with s square, okay, because that we've done before. So we could just look at s square, or 1/2 of s square, and see what happens, differentiate it and so on, right? Now, if we do that, we're going to have ss dot, right? And s dot will need to replace in the equation. Except here, we don't have b equal 1, right? We've put this Jacobian term here. So we're going to have, if we do this, we have ss dot, and s dot will have 1 over j times a bunch of things. All right? So to avoid that, instead of this, we're going to use 1/2 of js squared. Well, maybe there's no need to. So instead of 1/2 of s squared, we're going to use 1/2 of j s squared. Okay, I'm going to add the j here in v. Okay. Now you might say, I don't know j, that's fine, because it exists, right? So we can still do proofs on it and derive algorithms as long as our algorithms use known things. It's fine, okay? So I don't know j, but you might say also I need v to be lower bounded. Yes, very good remark, but you don't know j, but you still know one thing about j. It's positive, right? Because it's an inertia. So this will still be positive, although we don't know anything about j, except it's an inertia, right? So it's OK to start like this. This, for the moment, is just to avoid dividing by j everywhere, right, when we compute s dot. All right? OK. So let's do this. So what can we say about j times s dot? Right, we're going to have, if we differentiate this, right, we have s j s dot. So what can we say about j times s dot? Well, is j times x double dot minus x double dot r. Right? So now jx double dot is the dynamics, right? So we can rewrite it here. It's u minus bx dot absolute value of x dot minus mgl sine x. Okay. So we have u minus j x double dot r minus b x dot absolute value of x dot minus mgl sine x. All right? So this is just replacing. Js dot, right, is j x double dot minus x double dot r. Jx double dot is u minus bx dot absolute value of x dot minus mgl sine x. And then we have the jx double dot r. All right? Okay, and this is because we need this js dot here. Okay. Now, let's look at this structure here. What can we say? This term in JS dot, which we're going to have in V dot, right? It will be equal to the control input minus these things. Now, each of these things is really has the same structure, is the product of something unknown and constant, like J, B, or MGL, times something known, like, and actually time varying, state dependent, and so on, like x double dot r, x dot absolute value of x dot, and sine x. So we see that this whole quantity here can be written as minus a bunch of known time varying and state dependent quantities, x double dot r, x dot absolute value of x dot, sine x, times J, B, and MGL, which is precisely what we called the vector A. Okay? So this whole thing, SJS dot, is really S U minus Y times A. Okay, where Y is going to be this matrix in the bracket, okay? This matrix is Y. So everybody follows this, right? We just did the algebra, so we differentiate this term, we get JSS dot. So the JS dot term we can expand easily using the dynamics. We still have the J double dot X term coming from the derivative of S, and so we end up with this. Each of these terms is the product of an unknown constant component of the vector A, A1, A2, A3, and a known time-varying state-dependent quantity. So if we put all the known quantities into a matrix Y, so the matrix Y is this bracket here, and it's known. And of course, this matrix Y multiplies this unknown vector A of unknown parameters. Right? So we are here, and U equal, V dot is equal to S times U minus YA. Okay, everybody follows this? Okay. Now, so let me rewrite this equation here, okay. J S dot is equal to U minus Y times A. Okay. So suppose now that we say, okay, so we'd like V dot to be negative. All right? Now, let's assume just for one moment, of course, you know, if we just did that and went home, we wouldn't have learned much today. So assume just for one moment that A is actually known. Okay? What would we do if we knew the parameters? Okay? Well, we could pick U equal YA, right? And then we could add some, for instance, a linear term like K times S, where K is a positive constant. Right? Suppose A was known, right? we could just use u to cancel this ya term, and we would replace this by some constant, so we would get minus ks square, right? And then, of course, it would be very easy to finish. You know, v dot would be negative. It would be easy to check that v double dot is bounded because v is s square. So if the desired trajectory is bounded, it means the state is bounded as well. And so every term in v double dot will be bounded. So v dot equal minus ks square will imply that s tends to 0 using Barbala's lemma. Well, will imply that v dot tends to 0, but v dot is minus ks square. Okay, let's be maybe more precise. So we'll imply that v dot tends to 0. But v dot is minus ks square, so that implies that s tends to 0. But s tends to 0 implies that x tilde tends to 0 and x tilde dot tend to 0. Okay. So if a was known, we could just cancel these nonlinear terms, add a linear term minus ks, and then using Barbala's lemma, we could do it in simpler ways also in this particular case. V dot equal minus ks square gives us v dot tends to 0, which gives us s tends to 0 because v dot equals minus ks square, and k is 17, right? And s tends to 0 implies x tilde tends to 0. All right? So if the parameters were known, not surprisingly, we could just cancel the dynamics and replace it by something simple, and we would get tracking error to tend to 0. Okay? Is that fine? Okay. Now, of course, you know, again, if we stopped here, you wouldn't have learned anything very interesting. Okay, it was just to start. Okay? Okay, so is that clear? Now, of course, forget about that, right? A is not known. A is not known, so, well, what could we do? Try to do our best approximation of what we just did. In other words, in U, we can't use A, but we can use an estimate of A. Let's call it A hat. Right, so what happens if we do this? Well, instead of minus ks square, we're going to have an extra term, right? And what will this extra term be? Well, instead of ya minus ya, now we have ya hat minus ya, right? So we get s y a tilde, where by definition, a tilde is our estimate minus the real thing. It's the parameter estimation error. Okay? So now a hat, instead of ya, we have ya hat. So instead of canceling as minus ks square and nothing else, ya minus ya, we have minus ks square plus s ya hat minus ya, in other words, s y a tilde. Okay? Is that clear? It's just algebra. All right. So, where are we? We tried to guess of a Lyapunov-like function. We picked basically s square. To make algebra a little simpler, we, instead of picking s square, we picked js square, not to have to carry around this j inverse everywhere. Okay. We did this computation. We chose our control law to do its best to cancel the dynamics, and then replace by something simple and linear. Remember, ks, right? S is this sum of position and velocity, so ks is like a PD controller, right? So we picked this to add to this cancellation, right? Now, if a hat was equal to a, we would just have minus ks squared, and then, of course, it would be very easy to finish the proof that x tilde tends to 0. But, of course, a hat is not equal to a in general, so we have this extra term sya tilde, which can be of any sign. Right? And remember, of course, we want v dot to be negative, so that's a problem. Okay. So what's the idea here? The idea is to say, well, you know, these Lyapunov or Lyapunov-like theorems are very simple to explain, and they give us a lot of flexibility in choosing our Lyapunov function candidate. Okay? Actually, in a sense, they give us too much flexibility. It would be nice if the theorems told us, well, you know, you can pick this candidate and so on. They say, well, you know, assume that you can find a candidate, then this happens. Okay? But on the other hand, it says you have all the freedom you want to pick the candidate as long as it verifies this. All right? So the idea here is, can we add a term to this Lyapunov-like function candidate, this Barbala's function, if you want, okay? Such that if we differentiate this term, we get rid of this term. Okay? Why? Because, of course, if somehow we can add a positive term here, whose derivative is minus this, right? Then v dot will be equal to minus ks squared, and the rest of the proof will be the same. Because then we could still use this, right? So the question is, can we add something here plus what? Okay. So that we get rid of this term. Right? That's the question. Okay. Now, there's lots of things we could do, right? Or we could think of. Perhaps the simplest is to say, okay, here I have s squared, which is my measure of tracking error, okay? I've chosen it well, so it's a first order problem and so on. That's my measure of tracking error. So to this s squared, I'm going to add a measure of parameter estimation error. Right? I don't know my parameter estimation error, of course, otherwise, you know, I would know the parameters. But again, I can use that in a proof as long as the algorithm doesn't require this information. Okay. So basically, we're going to put a tilde square here, except to make it a little more general, we're going to add a constant positive definite matrix, which I'll write P inverse because I happen to know the result, and the result will be simpler writing it P inverse, but simply a constant symmetric positive definite matrix times a tilde. So this extra term I'm going to try to use simply a quadratic term in the parameter estimation error, the same way I had a quadratic term in the position error. Okay? And P is just a weighting matrix. If you want, for the moment, you can just think of it as a diagonal matrix, if you want, with positive coefficients. Okay. So, now, before we do this calculation, remember, the idea is that if we do things right, perhaps, right, by differentiating this term, we'll find a way to eliminate this term. Now you might say, why didn't we add just the integral of minus this term, right? Which that would be fine, except we have no idea of its sign. So we wouldn't be able to say that v is lower bounded. So that's why we do this. So the idea is we're adding this term and we hope that somehow we can play with this to cancel that. Okay. Now, before even getting into the somehow, what is this idea assuming about a hat? What is a minimal requirement on a hat for this idea to have any chance to work? Suppose that, this is it, it has whatever numbers, and I pick a hat, which is 17, 4, 23. That's it. Will this work? Why? Because if we want the derivative of this to cancel that, this better be time varying. Right? If we pick a hat constant, since a is constant and p is constant, the derivative is 0, and this was just nice colors, okay? So for this to work at all, okay, it means that we're going to need a hat to be time varying, a tilde to be time varying, and therefore, since a is constant, it means that a will have to be a hat will have to be time varying. Okay. All right. So now we have the derivative of this. So by now we've done this before, right? We've done computations like this before. So we have the derivative of a quadratic form, right? So 3 terms. So it gives us 1/2 of a tilde dot p inverse a tilde plus 1/2 of a tilde transpose d over dt of p inverse a tilde plus 1/2 of a tilde transpose p inverse a tilde dot. Just the derivative of a product of 3 terms, okay, with the 1/2 getting out of that. Now, this term is 0, of course, because p is constant. So we have 1/2 of a tilde dot transpose p inverse a tilde, 1/2 of a tilde transpose p inverse a tilde dot. Can we simplify this a little? Well, again, these are scalars, right? These are scalars. They are derivative of scalars, so they're still scalars, right? So they're equal to a transpose. So if you take the transpose of this, you find a tilde transpose p inverse, because p inverse is symmetric, a tilde dot, which is exactly this, right? So in other words, because these are scalars, this first and this third term are equal, right? One is the transpose of the other, and therefore they're equal. And so what we get is a tilde dot transpose p inverse a tilde, right? This and that, if you take the transpose of this, for instance, you find this, or equivalently, okay? And so you can write them 1/2 plus 1/2 as this, okay? And just as the blueberry on the cake, right, or whatever, you can also say that a tilde dot, since a is constant, a tilde dot is simply a hat dot. Okay? Since a is constant. Okay? So here we are. We can add this term here. 1/2, no 1/2 actually, sorry. A hat dot P inverse a tilde. Same term here, same term there. Okay, everybody see what I did, right? I just picked this term and added it to V dot. Okay. Now, what do we want? We want this. We would like this plus S y a tilde. We would like this to be 0 because we want these two terms to cancel. Okay. So we can write this as A hat dot transpose P inverse plus Sy A tilde. And so how can we make this 0? Well, there's this thing called algebra, right? And so basically you're saying, well, A tilde is whatever it is, but it's multiplied by this parenthesis. And so I can just solve the same way I played with phi dot last time, right? I can just solve parenthesis equals 0. And what will it give me? It will give me A hat dot. A hat dot is equal to minus P Y transpose S. So if we want the parenthesis equals 0, we can solve it as A hat dot equal minus P Y transpose S, which I wrote here. Can we do that? Absolutely, the same way we hadn't defined phi before last time, and we chose, to define it a certain way to make an equation simple. Here is the same thing. We choose A hat dot in a certain way to make this parenthesis to be 0, and therefore for that green term to cancel that term. After which V dot is equal to minus K squared, and everything works the same way. Okay. Everybody understands the algebra. We'll come to the interpretation in a second, but everybody understands the algebra, right? We had V, we started with 1/2 of S squared, 1/2 of JS squared. We had V of a certain form, plus some leftover term, which was due to the fact we couldn't cancel A hat exactly with A, okay, because we didn't know A. All right? This leftover term, we said, well, let's try to get rid of it in the algebra, right, by adding a term to V. And we just pick a quadratic term in A tilde, the parameter estimation error. We did the calculation, noticing, of course, we had to leave the flexibility for A hat to be time varying. Okay? And we ended up finding that if we add this quadratic term, we get this here. Now we wondered, can this cancel this, which would be ideal? Yes, we just have to solve the equation parenthesis var equals 0. And we get this. After which V dot is just equal to minus Ks squared as before, which implies, verifying that V double dot is bounded, which comes from the structure of V again, that V dot tends to 0, S tends to 0, X tilde and X tilde dot tend to 0. Okay? So what does this mean, right? It means we have the combination of two things. One, of course, is a control law, which does its best to cancel the dynamic parameters and replace them by something simple like a PD controller. And then we have the adaptation law, which is a differential equation, which you can initialize any way you want, for instance, at A hat equals 0, or any original guess you may have of the parameters. Okay? So this is an adaptation law. And this adaptation law basically feeds the control law, right? It gives A hat to be used in the control law. And so the combination of this control law, which uses A hat, and this adaptation law, which generates A hat based on state measurements and S and so on, guarantees that this use of Barbell's lemma works. In other words, that V dot tends to 0, which implies that X tilde tends to 0. So this says, starting anywhere, so you take an arbitrary desired trajectory, okay? You assume the desired trajectory is bounded and so are its derivatives. You take an arbitrary desired trajectory and you start with arbitrary initial guesses of the parameters. For instance, you can all initialize them to 0 if you want. And X tilde will tend to 0. In other words, after some transient, the system will behave as if you knew the parameters. Okay, it will follow the desired trajectory exactly. Okay. So if you do this, starting anywhere in the state space and without any a priori information on the parameters, you basically have the system follow the desired trajectory as if you knew the parameters. All right? Now, remember I said originally this is not an entirely new idea coming from linear systems, because when we do PID controllers, we do something very similar. Suppose we just had a constant, right? Suppose this MGL sine x was just a constant. So it was, let's say, plus, let's say, MGL. There was no sine x. All right? Then the corresponding adaptation term, assuming a diagonal p, for instance, would just be, the y would be just 1, right? There would be, instead of sine x. And it would just be the corresponding term, a3, is equal to the integral of s times a gain. So exactly the I term in the PID controller, right? So you see this is a generalization, if you want, of a PID controller, all right? If the corresponding term was a constant, you would just have a PID controller. So if you want to belabor this point, which may not be entirely necessary, right? But you could also write u is equal to minus ks plus y a hat, and a hat is the integral of p y transpose s over time. So it's really a PD, if you want, and an I term, except of course the I term is using all the nonlinearities. Okay. Well, the only thing I did is I replaced a hat. I just wrote this equation as a hat equal integral of that. Okay, that's all. And replaced a hat in this expression. Right? This is really not necessary to write it this way. Okay, it's just to emphasize this PID analogy. Okay, just saying if you replace a hat in here by integral of minus p y transpose s, you get this. Okay. You have a question? No?
Yeah, we were wondering, the parenthesis is equal to 0.
Mm-hmm. Yes.
What's the parenthesis referring to in that?
Oh, this parenthesis. Sorry. This parenthesis, right? Because it's multiplied by a tilde. We don't know a tilde, but as long as we make this parenthesis go to 0, it's fine. Okay? Any other question, right? So you see, it's actually quite simple, and it actually works extremely well too, as we'll see. Is just very simple ideas of adding a quadratic term to the Lyapunov-like function to cancel the leftover term as best as we can. Okay, and then we see here we can cancel it exactly. And basically have the system behave as if we knew the parameters. So we'll do much more about this, but any questions so far? Yes?
They also depend on P?
Okay, so that's a good question. So for instance, these work, by the way, very well for robots as well, and so on, so multidimensional versions of this. Okay, so there's various ways that A could depend on T. Okay, A could just change abruptly. So for instance, if you pick a load, or you catch a load, right? You catch something. So A changes. So then it's fine, because from the time you securely grab the thing, you can just see this as T equals 0, and from then on A is constant. Okay. 2, if A changes slowly, quote, with respect to everything else is going on, so in other words, perhaps it has to do with how much the thing heats or something like that. So it's changing slowly. Then you can, for the purpose of this, you can assume it's constant, and it will basically keep working, keep adjusting if you want to do A. If A is changing more or less as fast as the rest of the system, then it has no reason not to be considered as a state, right? Why not give it state status, right? If A is changing as fast, then you want to model it. Okay, maybe you want to model it as a function of other unknown parameters, right? but who are reasonably assumed to be constants. Okay. Any question? Okay. So this is the basic idea, if you want. So we're going to do a number of things. We're going to extend it to the multidimensional case. We're going to see how it combines with just the robustness idea. Okay, in other words, suppose I have some other terms here in the dynamics which are not depending on constants, right? But I can estimate and then bound the estimation error. What do I do? And so on, okay? Before we do this, we're going to do something that we don't really have to do to use this and so on, but so it's a kind of a remark, if you want, but it's kind of an interesting remark, which is, bless you, so, in other words, this is kind of an aside. You don't need to know this at all to make this work, but it's, in a sense, something which is interesting to realize. So I've just said, you know, using this adaptation law, you can make the system behave pretty much as if you knew the parameters. Okay. Now, does this, and whatever happens, you guaranteed that the trajectory tracking error goes to 0. Okay. The question I want to ask, which is kind of a side question here, is does this imply that A hat converges to A? Okay, so yes. How many think yes? Okay, how many think no? Okay. All right. So why doesn't it imply that A hat converges to A? Because it depends on what you're trying to do. Okay, so suppose we take the robotic version of this, okay, so you have a 7 or 8 degrees of freedom manipulator, let's say, and you have a load, and the task is to stay there. Right, that's the task. Now, to stay there, what should you do? You should do nothing, okay? Apply zero control input, gravity is taking care of it, okay? You apply zero control input. You do nothing. In the process, what do you learn about the parameters of the robot or the load? Absolutely nothing. It's a feature, right? It's a feature. Why? Because if you wanted to learn anything, you would have to move, and I've just told you, stay there. Okay? Similarly, you know, if I'm trying to move this load this way, I have no reason to learn about parameters which affect only this motion in this plane, because it would detract me from doing what I'm doing. Okay? If the desired trajectory is so complicated that there's no way to track it, which I know I do, there's no way to track it without the parameters converging to the real thing, then the parameters will converge to the real thing. Okay? So what we'll see, it's a little like spy movies, you know. Adaptation is on a need-to-know basis. In other words, this is always going to guarantee that the task is achieved, okay? So in other words, this is always able to guarantee that this task is achieved. If the task is so complicated, so challenging, so rich, if you want, that there's no way to achieve it unless in the process you estimate the parameters exactly, then by definition, it will estimate the parameters exactly because you know you achieve it. Okay? So the notion there's several versions of this notion, so we won't detail the subtle distinctions. But the notion is what's called sufficient richness. In other words, as we'll see, if the desired trajectory is so complicated, so rich dynamically, right, that there's no way to track it without estimating the parameters in the process, then of course we'll estimate the parameters in the process. Okay. Okay, so now let me explain a little more. Now we may want to pick up another back of the envelope because this will be very imprecise. It's just to give you the idea. But it's the same idea that is used in the real proof, except in the real proof you have to put the epsilons and the etas in the right order and so on. Okay. So let me explain the idea. And by the way, so I said, again, I said adaptation is on the need-to-know basis, and it's a feature. It's not, well, you know, this is not fair, you're not estimating parameters. It's a feature, right? Because, you know, again, if you take the example of you don't want to move, well, you don't want to move, right? So you don't want to estimate these parameters, that's because you would have to move. Okay? So it's a feature. So let's see, what do we know? Okay, we know S tends to 0. Okay, so that's clear. We can verify easily S dot tends to 0. Why? Because you compute S dot and all the terms in S dot are bounded, which is, by the way, which is what is needed to show that V double dot is bounded. So, sorry, to be more precise, okay, S double dot is bounded. So if you compute S double dot, all the terms will be bounded. And so S dot will tend to 0 because of Barballa's lemma. Right? Remember, this was a specialized version of Barballa's lemma. But Barballa's lemma was saying in general, if you have a function, okay, which tends towards a limit and whose second derivative is bounded, then the derivative tends to 0. Okay? So we can verify that because S double dot is bounded, S dot tends to 0. So let's take this equation again, Js dot equal U minus Ya. And U equal Ya hat minus Ks. So we have Js dot plus Ks is equal to Ya tilde. Okay, so we have this equation, which is from here. We replace U by its expression. We have the minus Ks term. And we have A hat minus A, so we get this. Okay, everybody follows us as just the algebra. Ya hat minus Ya, that's Ya tilde. And the Ks we put on the left-hand side. Okay. So what can we deduce from these 2 points? We know that S tends to 0. It's easy to show that S double dot is bounded, and therefore S dot tends to 0. Js dot plus Ks equal Ya tilde. Well, Ya tilde tends to 0. Because J is the sum of two terms that tend to 0, right? And also, we know that S tends to 0, which implies that X tends to XD and X dot tends towards XD dot. Okay. So Y is going to tend also, so Y is this matrix here, right? But here sin X tends towards sin XD. x dot absolute value of x dot tends towards x d dot absolute value of x dot, and so on, right? So this matrix Y, because the trajectory converges to the desired value, this matrix Y converges to what we can call YD, namely the expression of Y where you replace the state by the desired state, right? So YD A tilde tends to 0 because Y tends to YD. All right? Okay. Does this make sense? Yes, because if you think of this equation, of course, if A tilde was 0, we just have a linear stable equation and S would tend to 0. Okay, we wouldn't really need Barbella and all these things, right? So now what's going to happen is you have this. S is driven by kind of a filter equation whose input is Y A tilde, right? So whenever A tilde appears in the form Y A tilde, makes sense because that's how the dynamics is, right? You have a scalar dynamics and 3 unknown parameters. So it makes sense that not A tilde tends to 0, only Y A tilde tends to 0. Okay. Now, similarly, Y tends to YD, so YD A tilde tends to 0. Okay. So, okay, so all of this, by the way, is correct. I'm saying that it's going to be a little more intuitive from now on. So, first of all, if we take this equation YD A tilde equals 0, it's an equation with, it's one equation with 3 unknowns, right? So the solution A tilde is not unique, which of course for our case means A tilde is not necessarily 0. Okay? 3 equations. We have one equation, 3 unknowns, right? So this equation saying that YD A tilde equals 0 doesn't imply that A tilde equals 0. Okay. So now let's look a little, we can write this equation by saying that the absolute value of YD A tilde is 0, or in the vector case, the norm of Y A tilde would be 0. Okay, so if we say that the norm of YD A tilde is 0, it's equivalent to saying that A tilde transpose YD transpose YD A tilde is 0. Okay, we've just taken this norm or the norm square, if you want. So we get this. And what can be said about this matrix? Well, it's a square, right? So it's positive semi-definite, but it's not positive definite in general, right? It cannot be because its rank is at most 1. Right? It's product of YD by YD transpose, so its rank is at most 1. It's a 3 by 3 matrix. Okay, so it's not positive definite, okay? Okay? All right. Now, so what is the sufficient richness idea about? It's saying, okay, and that's where you have to put the epsilon and the etas in the right order, and we're not going to do that. We're just going to give you the intuition. Okay. Let's place ourselves at t equal infinity. Okay. And we have this equation the parameters have converged to something. Okay, that's where the approximation, or at least the fact that it's not rigorous saying that way. Parameter has converged to something, but the trajectory keeps moving. Right? So the question is, of course, instantaneously, this matrix YD transpose YD has no way to be invertible. It is of rank 1, period. Okay? It's a 3x3 matrix of rank 1, so it cannot have a unique solution. Okay? However, if you assume in this intuitive approximation that the parameters converge but the matrix keeps changing, indeed at any instant it's of rank 1, but its time average could be of rank 3. Let me explain. Suppose I have a matrix. Let me take one matrix. At a certain instant, I have 1, 0, 0, 0, 0, 0, 0, 0, 0. So what's the rank of this matrix?
1.
1, okay. So suppose at some other instant, I have 0, 0, 0, 0, 1, 0, 0. Still have a matrix of rank 1. And at some other instant, I have 0, 0, 0, 0, 0, 0, 0, 1. Still have a matrix of rank 1. So instantaneously, all of these matrices, which could be YD transpose YD, right? All of these matrices are of rank 1. However, of course, if I take the time average of these matrices, I get 1/3 of identity, which is definitely not of rank 1. It's of rank 3. Okay? So the idea is, of course, instantaneously, this matrix is not full rank. But perhaps on time average, because the trajectory is so exciting, is so rich, it will cover full rank space. And if that's the case, then the parameters will converge. Okay? Yes?
So were we saying for any instant the matrix is definitely not full rank, or it doesn't have to be full
No,
rank?
it's definitely not full rank because it's a product. Here, think of it, in this case, it's a product of two vectors, right? So it has rank at most 1. And in a robot, we'll see that next time. You could have a 6-degree of freedom robot with 10 unknown parameters, so you'd have a matrix of at most rank 6 with 10 unknowns. So you can make this a little more formal, and we haven't proved this. I'm just stating the result, okay? So, and you have, in the book, you have references on, you have a proof of the result and references on the history of that result. So the result says A tilde, so A hat tends towards A if sufficient condition, okay, not necessary because there's lots of versions of this, okay. There exists some time t0, there exists some time window length t, and there exists some constant alpha, such that for any t larger than t0, the integral from t to t plus capital T of the matrix YD transpose YD is larger than alpha I. Remember, we said before, if you have two matrices, M1 and M2, two square matrix, when we say M1 larger than M2, it means that M1 minus M2 is positive semi-definite. Okay. Right, it's just a notation. So what does it say? It says from a certain time on, there exists a time window. Okay, this is the average over a window of length capital T. Right, this is the time average of this matrix, which is positive definite at any instant, but on time average, it could be positive definite. Okay. And therefore, it could be larger than some constant positive definite matrix. All right? So if that condition is verified, sufficient condition, meaning after a while, this is just that this may not be true for time equal 0, but you don't care. Well, you care about, you know, what happens at time t equal infinity. So after a while, it's true that if you take the time average of this matrix y dy, that time average remains larger than some positive definite matrix. Okay? And you see that this is a condition on, as I said, sufficient richness condition on the desired trajectory, xd of t, right? Because it's all entirely in terms of the matrix yd, which is the computation of this matrix along the desired trajectory. So, again, this doesn't require to know this at all, okay? Implementing the adaptive controller doesn't require to know this at all, okay? But it can be shown, and again, you have references for that in the book. It can be shown that if the desired trajectory is sufficiently complicated, sufficiently rich, in this sense, then the estimates will have to converge to the real thing. Okay. And actually, under certain simple conditions, they'll converge exponentially to the real thing. Now, you might say, well, who cares? In a sense, we just need this. Well, it depends on your application. You know, in many applications, you just need this, and you don't really need to know this at all. Okay. But in some applications, you may care really about the parameters. Okay. Including in some applications where you think of as just control. Okay. So for instance, suppose you want to throw an object, okay, somewhere precisely. What you're throwing is the center of mass, right? What the trajectory of the object, right? So what does it mean? It means if it's an unknown object and you want to throw it precisely, in the throwing motion, you need to find out enough about the center of mass so that when you open your hand, it goes the right way, right? So that's a case where you'll have to design a throwing motion which not only throws things right, perhaps at 45 degrees and something like that, but also learns enough about the position of the center of mass to adjust itself to throw the right way. Okay? So that's a case where you need parameter estimation, even though originally it sounds like a pure control problem. Okay? But of course, there's many cases where you're perfectly fine with this, and that's it. Okay? Now, we also see that these algorithms converge extremely fast. They are extremely effective. They work very well, and so on. Okay? And it's precisely because they do this adaptation on a need-to-know basis, right? So that basically they estimate parameters just to do the job. Okay? And this they can do very fast. Okay? So next time we'll see how to combine these ideas with just robustness, the rest of the dynamics, which may be just unknown but bounded terms or just estimated terms. Okay? And then how to apply it to systems like robots and spacecraft.